Hello, everyone. All right. So do we have Paul here? Paul, let's get your slides up. So we go with our format.
Can you see my slides?
Um, yes.
Good, excellent.
So just 1 second. I'll get this notes here and we'll start with the intro. All right. So welcome everyone to another OCP Tap session. This is now call number 98. And so today we have Paul Borrill. And let's see, where are my notes here? There you go. So Paul Borrill is the Chief Product Officer at Daedalus and an expert on software infrastructure. He contributed to the system development at NASA, Sun Microsystems, Quantum, Veritas, and Apple. Paul co-founded the IEEE Hot Interconnect Symposium and the Storage Networking Industry Association, SNIA. Also, Paul earned a PhD in physics from University College London. He's also founder of It's About Time Club, forum for physicists, computer scientists, mathematicians, neuroscientists, philosophers, and practicing engineers to explore our unfolding knowledge of the nature of time and causality. So today's talk is about the clock coherence from terrestrial microdatacenters to interstellar. And with no further ado, Paul, the floor is yours. You're muted, I think.
Yes, you're right. I was muted. All right, thank you. Let me get started.
And for everyone else, please keep your microphone muted so we'll have no interrupts.
Well, thank you, Ahmed, for inviting me. We've had some amazing discussions in the Mulligan Stew meetings, thanks to your participation, and I hope that we have many more. And thank you, everyone, for coming today and lending me your ears for the next hour. I'd like to get through the presentation first. We should take about 30 to 40 minutes, and then we can take questions. So my name is Paul Borrill, and as Ahmed said, I have a background in system architecture and performance measurements in several Silicon Valley companies, including Sun, Quantum, Veritas, and Apple. But my obsession with dependable computing started after I put an experiment on the last successful flight of the Space Shuttle Challenger. I am now on my third company trying to realize the vision of simple, resilient, and secure infrastructures. So this talk is joint work with Jonathan Gorard, and this particular talk was given a year ago at the Asilomar Microcomputer Conference, but because of the rules there, we weren't allowed to record it. And this version has been expanded with the help of Dugan Hammack and other members of our team at Daedalus, and also Witold Kinsner, who graciously reviewed this with me and helped improve it substantially. There are several folks in the audience who know my work, including Dugan and Witold, and folks from the It's About Time Club, and I'm sure they will be able to chime in at the appropriate time when they have questions. So my motivation today is to get people thinking about the nature of time and causality, as far removed as possible from Earth's TAI, atomic time, and GNSS, the Global Navigation Satellite System, as far removed as possible to expose our hidden beliefs about the nature of time. And I originally tried to pack everything into one talk, and I discovered that wasn't possible. I had way too many slides. So I'm going to give this first episode, which I call the what, starting with the question, is clock synchronization sufficient? Episode 2 will be about the why, what need in the industry drives this motivation. And episode 3 will be how to manage events and interactions from distributed systems to swarms of spacecraft on their way to Proxima Centauri. The bottom line here, to be spoiler everyone, is clocks must be autonomous, they must be symbiotic, and they must be digital twins of each other. And the challenge is how to manage stochasticity. And for those of you who would like to solve impossible problems, let's give you a quick hint here. We think the solution lies in addressing indefinite causal order, which is a big issue today amongst the physicists. So here's the bottom line. Clocks can't be synchronized without interactions, but they can be disseminated. We know that simultaneity planes don't exist, except in a frozen empty universe. Einstein proved this over 100 years ago. So why do we still think that we can synchronize clocks? Well, NTP and PTP are trees. And all you need to do is be careful about how you choose your route and how you do failover, especially. It is a mistake to continue to believe physics doesn't apply because it's restricted to low relative velocity or atomic scales. Neither of those two statements is true, either in special, general, or quantum mechanics. And a nice takeaway from this talk would be that irreversibility is in the eye of the observer. Because what we know from all of our physics experiments and theories is that space-time doesn't behave that way. Entanglement and indefinite causal order are the new aha moments in physics. This is 100 years after Einstein. So how might be this related to problems in distributed systems? And why databases silently corrupt data with their transactions? Well, we believe that it's essential, and we can do this with our engineering on networks, that these elements must interact with dynamical behavior. And we can talk more about this in episode 2. It's no more possible to predict the past than you can predict the future. This is a very important finding in the mathematics of systems. In a nutshell, the horizon of predictability is the same in both directions of time. We will talk about this and this how and more in episode 3. So last year at this time, Robert G. Kennedy III asked me to give a talk at the Asilomar Microcomputer Conference, workshop, AMW as it's known, on how to synchronize clocks. He was aware that I'd given talks at Stanford and other places on the nature of time and causality, and that I was also running a podcast series called It's About Time. Now, it's been a huge honor to be the host of this podcast series called It's About Time, and many professional scientists and mathematicians and engineers have really helped me come to my understanding of this through that podcast. That podcast had been put on pause right now because we were getting a lot of far too many attendees, and we couldn't manage the curation of the transcripts and everything. So we moved this to a weekly meeting that was called Mulligan Stew. But you can still click on most of the blue links in this presentation, including pictures like this, and you will take you to the website and references, and we hope to get that updated shortly. One of the people I interviewed was Anne Curtis, who was at the National Physical Laboratory in the UK, and she's one of the world's experts on atomic clocks. And she gave a talk, Timekeeping in the 21st Century. What are atomic clocks? And she introduced me to her friend Giulia Rubino, who's a theoretical physicist, who talked about causality and the arrow of time in the quantum world. These were absolutely eye-opening conversations for me. For example, one of the experiments they were involved in is measuring the stability of fundamental constants with a network of clocks. The bad news and the good news is that they are the same. They found no statistically significant deviation in what we regard as the fundamental constants of nature. So that's the good news. Now, the bad news is there is no now. This is a very famous paper in NACM, I think 2015. If you're a computer scientist, this is probably as far as you've got in learning that time in computer science is not Newtonian. And if you haven't read this paper, I thoroughly recommend you go back and read it. So how do we begin? Let's start with a photon. When they travel from the beginning of the universe and they land on a detector on the JWST, photons are arrival events. So in being able to understand how we manage this swarm of spacecraft that we want to send to the nearest star, Proxima Centauri. Sorry, did someone have a question? Can you please turn your microphone? Thank you. So let's take this metaphor and see how far it will take us in managing this swarm of nanospacecraft 4.25 light years from Earth to our nearest star. So the first thing we need to realize is that swarms in formation still require some kind of synchronization. The first thing you have to ask, if all time is a tree, is, well, who should be the root? In computer science, it's convenient to presuppose centralization. This doesn't work very well in data centers, and it absolutely won't work with a swarm of micro or nano spacecraft 4.25 light years from here. So we need a protocol that goes beyond simplistic consensus, where we elect a leader, and a hint to engineers is we need to complete redundancy. Not only can any cell become the controller, all of the cells need to manage their own causal trees. There isn't just one tree. So that's why we're going to lead the conversation and go back to the basic questions of this premise that Robert Kennedy had. If clocks can't be synchronized, then how do you coordinate the activity of a swarm of spacecraft? Can a laser push them to 20% of the speed of light? How do we align the swarm to transmit data back to Earth coherently? And how do we repair in flight and on the way to Proxima Centauri? So calculating the photon spectrum redshifted by 20% of C, that's, we should be able to do that as long as we can detect the frequency of that photon. And we know that that's a difficult problem unless you integrate over long periods of time. But we can also calculate, for example, the subtended angle of the transmitter and receiver rays. And the big question is, what kind of network architecture is needed? So let's begin with what Jonathan Gorard and I came up with. Typically, when we speak of synchronization within distributed systems, we mean getting all the nodes to agree on a single numeric value. We call this, let's say, clock time. Now, in principle, this can be done within an inertial frame with a fixed network topology and when all the redshifts of those photons are calculable. For example, if Alice sends Bob a packet containing her clock time and Bob receives it, he sets his clock time to the same value and uses the redshift of the incoming packet to calculate the Lorentz transformation between the two signaling positions and also back to Earth. But the problem is realistic frames are non-inertial. Realistic redshifts are not always calculable, and realistic network topologies are not static. This is true in both data centers and distributed systems have to put up with this all the time. And it's also true in swarms of satellites. So for example, in a rotating reference frame, even within special relativity, the Einstein synchronization convention no longer makes sense. The synchronization relationship becomes non-transitive. In other words, if Alice synchronizes with Bob and Bob synchronizes with Charlie, they achieve a different synchronization than if Alice synchronizes with Charlie directly, and therefore it's path dependent. Now, in full general relativity, with dynamic network topologies, the problem becomes much worse. But who cares about clock time? All we need to know is the causal structure, which events logically depend upon which other events in our algorithms. So let's simply just redefine synchronization to mean agreement of the causal structure as represented to a partial order or directed acyclic graph. I'll use the word DAG several times in this presentation. This needs to be managed and maintained across all the nodes in the network. The causal graphs perceived by different nodes may temporarily be non-isomorphic, but we can design communication algorithms that provably guarantee that they will eventually become isomorphic after not some arbitrary clock time, but after a finite and bounded amount of communication. So for example, we can achieve something called confluence, causal invariance, or what the computer scientists like to call eventual consistency, for example, with guarantees rather than probabilistic, asymptotically approaching something with an indefinite number of redundancy. So this new notion of causal synchronization, although strictly weaker than the old-fashioned clock synchronization, is all that is needed to guarantee correct ordering of packets, which means that we can then prevent the data loss that we're seeing in data structures when we try to do transactions, and all of the other desirable properties that one expects from a distributed protocol. The algorithm that guarantees eventual consistency requires only a minimal modification of network time protocol, effectively replacing clock time with a DAG structure. And it works in full general relativity with dynamic network topologies as defined through a graph rewriting system and with no assumptions regarding the underlying space-time structure. Whatever space-time is doing to you, this particular algorithm and structure should work. So what does it look like? Well, let's take these. I'm going to spell these out. I hope I'm speaking this only because I want everyone to know what the key points are here. We're trying to go through them very carefully, make sure no one misses something, either because they think they already know, or because they're perhaps a lot younger and they would like to know. So I'm going to speak these pieces of the slide here. So this very basic path-like network topology is in which all the nodes initially agree on the same, let's say, a trivial causal structure. And after a packet is sent from left to right and acknowledged by all the intermediate nodes, the causal structures perceived by different nodes are now different. This is not hard to worry about or to argue with. I mean, any computer scientist realizes that, yeah, this is true until you do something else like the coordination. But it gets worse. Within arbitrary space-time geometry and incorporating the effects of packet loss, the perceived causal structure can become more or less arbitrarily different. And we've seen this happen in our simulations and also in real systems. So you can see this in the causal structures recorded one after one set of interactions in this figure. This is the problem. The collection of all possible observable causal structures by different nodes in the network can be parameterized by means of a multi-way system. Another person who has contributed to this work is Stefano Gergosio at Oxford University, who has been an honored guest a couple of times now in our Mulligan Stew meetings over the last few months. But with finite and bounded communication, the algorithm guarantees that all multi-way paths will eventually converge. This causal invariance, confluence, eventual consistency thing. So this kind of confluence can be seen in the models also of Stephen Wolfram's writings. And there's a link there on this page, as you see, that's in blue, which I recommend you check out. And this is something we'll go into in more detail in part 2 and part 3 of this talk. A more sophisticated example, the previous example was a chain, is when we look at a graph with a dynamic topology, which this swarm of nano spacecraft would surely have to deal with on their way to Proxima Centauri, things start to get ugly. After only a few rounds of packet exchange within a non-trivial space-time geometry, the perceived causal structures are now radically different. And like databases, each observer will see a different causal structure unless you have coordination, which is something the database people would love to avoid if they could. Won't go into the details of that. That will be in episode 2, the why. So if we take this multi-way evolution with all possible causal alternatives, which will happen in real systems, this evolution is just a big flipping mess. However, we can still use this algorithm because it succeeds in achieving eventual consistency with a finite and bounded amount of communication. So that's the kind of physics description to the problem. Someone got a microphone on. If you could turn off your microphone, please. Thank you. All right, let me continue. So our conclusion is this. All time is a tree. Be careful to pick your root, and be extra careful in dealing with failover, because otherwise all hell breaks loose and your applications will go crazy. At Daedalus, we've discovered that we cannot guarantee transactions without a protocol that conserves information. This means there is a symmetry somewhere, and we think this symmetry is in time reversibility. So the holy grail of distributed systems, which is exactly once semantics, is impossible unless we pair exactly once sending with exactly once receiving of packets. We call this Shannon pairing, which is as consistent as we can make it with the new physics of indefinite causality. So I'd like to describe some of the work I've really appreciated from Pauli Erker, who I think is in the audience, I don't know yet. And I'll go through this fairly carefully because I want to say this in exactly the right way. I'm going to begin by saying that perfect clocks are impossible. This is a conclusion that he and his team at Vienna and other places of academic excellence around the world have come to the conclusion on. And these words on the left-hand side here, straight out of this paper, which you can click on when you get the draft, when you get the slides in the PDF form. For timekeeping devices, all clocks are just witnesses of the macroscopic breaking of time reversal symmetry. Because they take forward in time, with the emphasis on forward. Those are thermodynamic processes, and therefore inherently stochastic and never perfectly predictable. And the rub, as far as the synchronization of clocks world is, even an idealized perfect clock, even an ideal clock could never be perfect, simply due to the fact that the clock itself is fundamentally driven by stochastic processes. Remember that discussion earlier on about Giulia Rubino, and she did a PhD on the indefiniteness of the direction of time. Thoroughly recommend everyone reads her thesis. It's a beautiful piece of work. All of these words and the excellent stuff on this key paper, but I'll give you a feel here from one of the pictures in this paper. What you're looking at here is a stochastic arrival of photons. These aren't integrated over time. These are individual photon events arriving. And you'll notice that the more of them that you have, the more they appear to look like a Gaussian, which all signaling processing people and physicists kind of understand this picture. But there's no underlying background of time that all of these things are tied to. And what we have to do is say, well, what's the alternative? Well, instead of trying to have some big clock in the sky, which synchronizes everyone else and everyone has to be a slave to that clock, or I think these days I should call it a follower of that clock. What we have to do instead is say, well, okay, what if you were 4.25 light years away from Earth and you can't synchronize with Earth's TAI? Well, there is this wonderful paper that Pauli Erker pointed me to called Quantum Clocks and Their Synchronization. It's called the Alternate Ticks Game. And so within Newtonian theory, there seems to be no fundamental limits to the accuracy at which clocks can be synchronized. That's what, in Newtonian theory, gives us this intuition, which is incorrect, of a global notion of time. A notion of global time is also assumed in the usual treatment of quantum mechanics. And that's another different issue because it's parameter time there, not some kind of like background of time, but it's still, you have to parameterize it against something. And that's problematic in quantum mechanics too. However, the global structures have various non-trivial features which are a topic of ongoing research, and the community is doing a fantastic job of this. So generally, this global notion of time is just not achievable in any relativistic theory. And this wonderful paper describes, how we like to try and think of these things, and what we need to perhaps do in our networks and algorithms to be able to achieve these causal DAGs that I'm describing. So what else do we need for the journey to Proxima Centauri? Well, first of all, we need to get the power dissipation down. We need to use every trick in the book to manage energy. And the first one is perhaps the most important, which is reversible computation and reversible communication. Michael Frank, who I believe is in the audience today, is the world expert on reversible computation. He works at Sandia National Labs. We also need a distributed protocol, the wireless protocols that these satellites talk to each other with, and especially the wireless packet encodings that combine extreme robustness with sensitivity to Doppler shifts and low power dissipation. I plan to talk to Muriel Medard about this. She is a professor of computer science, electrical engineering at MIT, and perhaps has more patents than anyone else on coding theory, and really has taught me a lot already in the one meeting I've had with her. And thirdly, when spacecraft are communicating with rectangle lengths, they can get this power dissipation thing for free, because you don't dissipate energy unless you erase information. So only when perhaps they're communicating over long distances does this Landau limit come into play. And one of my favorite talks was with David Wolpert, who is now at the Santa Fe Institute. So getting back to the engineering, what are we proposing here? This thing needs rooted DAGs. Every one of the swarm can be the root of its own tree. There are no pre-selected centralized nodes in this architecture. This is what we call complete redundancy. Any cell can become a controller if other fails, but it goes more than that. What's really going on here is that we can have any one of these nodes. The dark node is the network that it's controlling from its perspective. And what we're showing here is that you literally can have a very simple DAG failover protocol, which allows you to go through failure and fault and rollover and recovery without missing a beat. And this would make the application programmers at the top of the stack in your distributed systems very happy if you could do this. So we can talk more about the how and this is done, and the algorithms that make it work in future episodes. Just so you know, Daedalus is in the business of designing and building and deploying platforms for secure, reliable, distributed computing on the edge. We like to think that we're the world's most advanced way to reorder events in distributed systems, and our use cases include distributed microservices, on the edge, digital twins, interfaces to quantum computers, and now swarms of spacecraft on their way to Alpha Centauri. Or the local space missions that people may be interested in. We're currently talking to prospective customers to learn more about their problems in the corruption and recovery of data structures here on Earth. The references that you can see here are the one from Jonathan Gorard. They will be in the slide deck we send out, and the references from me are here. They're also in the slide deck. So at that point, I'd like to ask if anyone has any questions. It's now 11:30. I took just 30 minutes.
All right, so let's open the floor for questions.
So either everyone was brought to tears or they were stunned into silence. I'm not quite sure.
No, it's a fantastic.
Okay, go ahead. We don't need
No, I don't have a question. I just have a comment about Paul's comment. It's fantastic presentation. My mind is still turning about this. I have a lot of questions, but I want to kind of think of it before I ask you.
You're very welcome. Excellent.
So anyone else? I'll start with a question.
I have a question, Ahmed.
Yeah, go ahead, Asham.
Cool. So, how are you, Paul? Nice to see you again, and the excellent presentation. So, if you would like, if we have a data center and we use now BTP, NTP, and all of these protocols, so how you envision replacing this protocol with something else that conforms to what you are talking about?
So
Should
this
we
is
get rid of, should we get rid of all of this and do something else like some other transactions and
actually we plan to go very deeply into that in the next talk. But the simple answer is I was trying to help find a use case for the time card and for PTP and NTP. And I already have some experience from Apple 9 years ago, 8 years ago, when we tried to experiment and think through the whole problem of how do you synchronize clocks. And we realized that it's a massive failure problem, and it just gets more and more complex as you add on more and more pieces to solve what you think are the perceived problems. But what we realized is that there is a structure already in the configurations of not just the PTP and managing the grandmaster clocks and the boundary clocks and then the ordinary clocks. That hierarchical structure already exists in the configuration of the time card throughout the entire data center. So if that already exists, the next question is, well, what's the next problem needs to be solved? Well, that problem is PTM. How do you solve the last a few centimeters, going across the PCIe bus from a host processor, which might be an x86 processor, and have that talk to, something which is a trusted source of time on a PCIe card, for example. And that problem has been solved too. And Kevin Stanton has done a beautiful job of getting that relationship between the Intel processor and and what's going on in PTM on the PCIe bus to basically under control. But again, it includes configuration. How do you get the timestamp counter in the x86 to be a slave to the clocks? And it turns out that you can do the opposite. You can basically say, look, if you want to manage a subset of your microservices, perhaps in a data center, well, you could make one of those x86 processors kind of the temporary master and say, I am the coordinator, the orchestrator for this set of 100 or 1,000 or 10,000 nodes. And you can guarantee monotonicity that way. But we don't know how to guarantee monotonicity if you're doing the opposite. So this is a fairly hard problem, and Kevin has already given an excellent talk on this. Did I answer your question, Hussein?
Thank you.
So I think I want to just elaborate basically on Hisham's question and basically like this whole status. So it is not about replacing PTP or any of these things. Like basically, let's say in PTP, if you have the grandmaster and then everything basically goes to this hierarchy of going things. And let's say in that hierarchy, if something breaks from the top, that is like a choke point, a single point of failure, then the whole thing gets lost. While in Paul's approach or strategy, there is no, let's say, a hierarchy, a tree. Instead, you have multiple things. It's basically on a consensus going through things. Now, you want to run a software-based method and then deal with the consequences of less precision, or you want to do with hardware and benefit from the improved precision. That's up to you. That's your choices with whatever is available to you. Did I say it right, Paul?
Actually, I would disagree with you on the way you said it. We don't get rid of anything. That's right. What we've discovered is that what you have to have anyway for the configuration of all the PTP structure and the PTM, you can use the arrow and the head of that arrow on each of those links, which you have to configure anyway. You can use that as your structure to solve any of the monotonic issues that you're going to get naturally from your network behavior. So if you can control that DAG, which you already have in place from the configurations you do, then not only can you get precision you can actually get absolute causal dynamics on this system. But each node has to be able to fail over in a very structured and disciplined way when failures happen. And failures happen all the time in data centers. As you know, the links are constantly failing, and the nodes are constantly failing, and all of these failures in large data centers. It's not just a large data center issue, by the way. We've seen small clusters of computers actually have this particular behavior where packets are lost, dropped, reordered, duplicated, and that plays havoc with the algorithms that the distributed systems programmers want to do. So we think we can take you from a stochastic, increased precision world into a world where you can, at least locally, manage the causal structures perfectly. We call it determinism on demand. It's a different way of looking at the reliability of systems, because we believe that nines are not enough. You need a different way of thinking about determinacy.
Right. Another question?
A quick question.
Yes.
Well, Paul, thank you very much for a very, very nice, thought-provoking presentation, and stirring the many of the ideas that were considered to be solved or partly solved. I think that this is beautiful and tremendous opportunity to deal with the changeability and variability, not just stochasticity of this universe, but the unpredictability in the long range and maybe even short term. But there's also the hope that there is, in that approach, there is a horizon of predictability. It is not white noise. There is some correlation. And the ability to also deal with those changes within the horizon of predictability. Could you comment on the potential of that? Because all of the systems will have to become self-adaptive, recognizing the situation and finding the best solution, maybe even self-healing in that process of predictability. Could you comment on some of the ideas of the potential of your approach?
So you're absolutely correct. In fact, I have two particular motivations that have driven my life and why I am so obsessed by the idea of dependability and self-healing. The first was because I put an experiment on the space shuttle where I designed all the hardware and the software, not the experimental apparatus, just the computer side of it. And ground support software for this thing. And that was on the last successful flight of the Challenger. So I was, it was a traumatic event for me for the Challenger to blow up on the very next flight many months later, a year later. The second was I was involved in the emergency data recovery after 9/11. That gave me another impetus to say, well, hang on a minute, why is it taking 3.5 weeks to recover the data, and tens of thousands of companies go bankrupt and the president goes to war? It seems like there's a really important project here that I could get passionate about, and I did. And I have been ever since, and I'm now on my third company. But it's all about the problem that you were just describing, Mathilde. It's all about how do we understand the nature of time and causality so that we can make things absolutely reliable, and in a sense that, it's not just redundancy. You don't asymptotically get to be more reliable. You can actually make sure that a lot of the failures that happen, every day, every second, every millisecond in data centers, you've got dropped, delayed, duplicated, and reordered packets, which are the required way to look at it, because the network for you in a cloud infrastructure is a black box. So how do the belief that I think that needs to be challenged the most is that when you drop and delay and duplicate and reorder packets at layer 2, that you can recover the lost information in the layers above simply by doing a retry, a timeout and a retry. But what we've discovered, as everyone has discovered, is those create cascade failures, and those cascade failures often show up as timeout storms or reconstruction storms, and there's lots of different names for them. Limpware. You'll find that there's tons and tons of this very bad collective behavior that happens, and mostly it's because of this paradigm of timeout and retry. You can't basically assemble the right kind of Shannon pairing in the endpoints when you're spraying packets all over the place and trying to use bandwidth to solve the problem, because more bandwidth just makes the cascade failures more intense. And so I'll put all of these problems together. What we believe is a solution to this is, and we like to call it applied graph theory. And that's something that we're fortunate that the mathematicians have made such phenomenal progress on graph theory. Ethernet is now 50 years old, and there's so much been learned about graph theory from the original foundations of graph theory in mathematics, that we think there's tons of opportunities there to engineer a solution that can be self-healing and also self-correcting when some of these errors occur. Did I answer your question?
Yes, definitely.
Okay. Does anyone else have any questions? I have plenty more slides if any of you want to go on a bit longer.
I do have just a kind of maybe a partial observation / question, and that is the underlying thing about synchronizing clocks is the concept of like you said, shared time and so on, but the principle that's important is trust. And how can you, have you, in this kind of architecture, what kind of safeguards or what kind of improvements can be made to kind of improve the underlying trust?
That's a fantastic question. In fact, we struggle as a startup in trying to tackle this problem, not because we don't have a solution. We actually do have a solution. We have a very different kind of network structure, which doesn't have the vulnerabilities that conventional IP networks do. I remember speaking with Vint Cerf when I was at a conference 20 years ago now plus in Virginia, where we spent several hours talking after dinner, and he was my hero. I was so impressed with being able to have dinner with him and many people at the conference, and then go into this room and have a great conversation. He spent almost the whole of that conversation telling me about why IP was so insecure and that there's no hope for it. He completely demolished my faith in networks, and he has emphasized this many times to other people. The whole idea of having an any-to-any protocol, which is what IP tries to do, which is to go out and find the gateway to the internet. That's what all internet protocols do. Is they're always looking for the gateway to the internet. Now there is a translation that happens when you go from Ethernet, which is a layer 2, to this layer 3 thing going on. And I think a lot of the problems actually can be solved at layer 2 again. But it's a different kind of flavor. We gave a talk on this at the Chiplet Summit and very recently, only a few weeks ago. And I also met with a lot of people at the OCP conference. In fact, that's where I met Ahmed. So it was wonderful that Ahmed gave a whole day's talk on synchronization. I think Ahmed was kind of disturbed at all the questions that I was asking after all of the people there. But putting this all together, what we've realized is that when we move to a chiplet architecture, what used to be kind of like the complexity of a city and a data center is now going to be shrunk down to motherboard size, with still the same amount of complexity you have to manage. So the fundamental problem of managing trust is managing complexity. And so attacking that head on with like these old behaviors of Ethernet and IP, maybe things that we have to be compatible with at some level, because no one can get out in the world and do and boil the ocean and start things from scratch again. But what we can do is we can say, let's redefine the next version of, say, Ethernet to be able to solve this problem without timeouts and retries. That also means that you can solve it without having to go through a switch or a NIC, which is misbehaving. This drop, reorder, delay, duplicate, and the packets problem. We think this is inevitable. We think that the mesh architectures that drop out of this, whether these have a valency of 4 or 6 or 8, we think is an opportunity to basically build network infrastructures, at least below the local infrastructures, which can have hundreds or thousands of connected devices. This not only provides us a new opportunity to give you confinement of these packets, which is the trust boundary that you're looking for, because everything sneaks through port 80 in a network, and it's almost impossible. I know it's impossible with the conventional architectures to stop this happening. What we used to find in a previous company was that zero-day exploits would basically come through port 80. They would attack the applications. The applications would then they would embed. They'll get into the operating system. They would embed themselves and then erase the tracks of the logs, which they could be detected as having coming in. And these rootkits were everywhere. These rootkits just can hide themselves for days, weeks, months, and even years. And if you don't reboot your systems, you basically have these happening all the time. So there's a few problems here related to trust. It's an extremely difficult problem, but one step is to say, let's redefine the trust architecture. We need to have something confined inside a boundary and not just, one drawbridge at the front of the castle where all the barbarians, will come to the gate. What we have to have is something more structured inside this castle, because this castle is not allow, a few hundred maybe or 1,000 people. It's now tens of thousands or hundreds of thousands or millions of things that are interacting. But most of these things are interacting east-west in the data center instead of what we used to think of as north-south, which is the way to the internet. So we think there's an opportunity to work with the folks who are defining the front-end networks and the back-end networks and redefine that trust boundary in a different way that doesn't depend upon legacy compatibility with something that was designed 50 years ago. So I'm actually intended to talk about this a great deal in a future episode, but did I answer your question?
Yeah. And when you were talking, I was inspired. I thought of something. Maybe an approach to this would be like linear network coding, where you have, this kind of shared responsibility between all the nodes to pass packets, and you have a kind of a protocol there. You can invalidate, what you think is out of order, too late, incorrect or whatever. But anyway, just thinking off the top of my head. But thank you for the answer.
You're great. I'm happy to go into it in much greater depth. I don't want this talk to be about my company, my product. I want this talk to be about the problem. We really want everyone to be sensitized to the idea that assuming a Newtonian background of time is a hidden belief that we have in all of our computer science and in network protocols especially. And we have a statement, a name for this. We call it forward in time only thinking, or FITO. And it's an interesting way of looking at it, because I even find myself sliding down a slippery slope sometimes of forward in time only thinking when I'm writing code in Rust, or when I'm designing FPGA protocols in Verilog, and I have a team of 9 people right now that's working on some of this stuff. So we're building a simulation so that not only can we try out different architectures, but you can get immediate answers on whatever your theory of space-time is, whether it's Newtonian or whether it's simple special relativity, whether it's completely indefinite causality or general relativity. It doesn't matter. Whatever space-time assumptions you have, you can literally click a button on our simulator and we can show you how this thing behaves. One of the things that we're hoping to do is basically use these ideas like linear network coding, for example, on our tiles. We have a 3x3 tile as a fundamental unit of resilience in our system. But Whittle Kensner is actually solving similar problems for spacecraft. And one of the things that he's basically noticed is that there is this kind of like tent structure for a forward and reverse ways of thinking about time, and a profound realization that we can't predict what was in the past any more than we can predict what's in the future. And this is a mathematical result, and it's beautiful. It fits in with everything to do with our intuition. And so this notion, biggest reason why everyone is looking at redefining layer 2, and there's a few different initiatives going on right now around the world in different companies. Some of them just want to try to make Ethernet the big winner again in the marketplace, and some of them have other motivations, but they all suffer from the same problem. When you try to use more bandwidth to be able to reduce, for example, the tail latency, you find that you increase the likelihood of these cascade failures. And long before you get the cascade failures, you're getting hidden, uncorrectable corruption of data. And you don't know that because when the NICs are receiving packets, they can't hang on to them. They've only got two choices: forward them, or which means up to the Intel processor, or drop them. That's their only choice, because these damn packets are coming in way too fast. So while theoretically it seems reasonable, like we've done for several decades now, to have indefinite length buffers, and all we need is longer buffers or whatever else, that doesn't work. It turns out the buffer bloat just makes latency terrible, and you really need the absolute minimum buffers possible. And when you do that, you can't hang on to the temporal intimacy between packets long enough to be able to repair those breakages in Shannon pairing. Did that answer your question? By the way, do I call you Bijan or Bijan, or how do you pronounce it?
Bijan, yeah, I answer to anything, so.
All right, thank you. Well, I've still got 7 minutes left. Any more questions? I can see that Edward Lee's in the audience too, and he's someone who's familiar with that. Anyone else?
I guess one thing I was wondering too, another thing, I'm always wondering something, but it's like, have you considered what the community can do for you? Like, how can we work together to kind of open the door, or jump over a roadblock, or do something? I mean, because understand that you are pursuing, your thing and your enterprise, and that's great, but I think we could work together, right? And kind of jointly solve universal problems.
I would love to do that. I do have a history of starting off initiatives that tend to have big impact on the industry. One of them was I was the founder of the IEEE Hot Interconnects conference. That was a long time ago, and I recently went back and looked at them about 5 or 10 years ago, and these guys are doing well. It's a great conference. And I was also, because of my frustration with the IEEE committees, because I used to be the vice president for standards for the IEEE Computer Society a long time ago, and out of my frustration at how slow that was, I founded the Storage Networking Industry Association. So I have a saying, there's no limit to what you can achieve if you don't care who gets the credit. And that's my MO. I like to get things working together. When I see a problem and I see some potential solutions, and so working with you, Bijan, would be fantastic. You've got your fingers in the pies of all of these different initiatives going on at OCP. We should have a private conversation, and perhaps including Ahmed, about how do we turn this into an initiative that the industry can appreciate and benefit from.
So,
Absolutely.
Paul, do you think you can have a demo similar to the one you provided in Chiplet conference in the next global OCP summit?
Yes. Well, so first of all, we already do have a demo. It was demonstrated at the HotNets conference in June of last year. And that was between real servers with real SmartNICs, with FPGAs, with optical connections. And what was fascinating about the result is it took me forever to persuade our engineers that that you should design the protocol this particular way. It's actually, it really isn't much more complex than the alternating bit protocol, but you have to have a warped mind like mine to try to exploit that. And that's what we discovered is if you don't try to push too many packets down the wire and stack them up and queue them, which is what causes all the cascade failures, then what happens is you can guarantee that you're never putting a packet on the wire that can't be received by the receiver. And that's halfway towards exactly one semantics. So we demonstrated that in June last year. It's been demonstrated, all working beautifully. What was amazing was that the particular cards that we were using, these were the SFPs that we were connecting at 10 gigabit between these cards. One of them was actually really flaky. And what we discovered is that our protocol did exactly what it's supposed to do. It basically, it didn't just do a retry. It reversed the transaction. In other words, instead of sending something, we have an unsend. Instead of transferring a piece of information from Alice to Bob, we have an untransfer. And so it turns out this notion of reversibility absolutely addressed this flaky NIC card beautifully. And I was quite proud of it, that it really worked as well as it did. Now, we actually moved to a tabletop demo. In fact, it's in my kitchen back here that Sahas and Dugan are working on. And that is basically continuing to develop the actual protocol and the testing with a tool chain for FPGAs. But we're rapidly moving into the point where we need a lot more capital equipment. And so we're basically going to have to go out to investors to be able to try and get some capital equipment and maybe some space in a data center, because, you know, after all, servers are pretty loud. I'm sure they will be too loud for inside of my house. So we're going to want some capital equipment so that we can really expand this out. Maybe only half a dozen machines to begin with, but then we're going to need a dozen machines soon after that, and within 6 to 9 months we're going to need like 25 machines. So we have a development plan. We're underway. We have a team that's doing great. So what we're going to have to do now is to actually construct the use cases and the business plan that VCs want to see. And the first thing they want to see is knock down the technical risk. Knock down, can you light the hardware? Is this thing feasible instead of just slides? And then the other side of it is, can you knock down the market risk? Is there a customer that you can point to or more who can validate that they're solving the right problem? And we're happy to say that we're talking to 3 customers already, and a 4th one is underway right now on trying to understand their problems. So we feel like all of this is coming together beautifully. It represents over a year's worth of work by our team to get ready for this. And we'd love to talk to some more people, not only about collaboration, but also about who has the kind of technical expertise, to help us with the tool chain for the FPGAs. So Hisham, I hope I answered your question.
So in a nutshell, you will not be ready for a demo in October during the global summit.
Unless we get at least one more person to help us on the team and access to the capital equipment that would demonstrate what we're doing, because we don't want to just show last year's demo. We want to show significant progress. We know where this protocol is going. We love to talk to the folks who are working on PTM and on PTP. We'd love to talk to them about how to automate the configuration of these DAGs, which you need anyway to manage the hierarchy of clocks.
But maybe demonstrating the main concepts you're talking about will be enough and will be stimulate discussions about all these ideas, which is useful for you too and your team.
In time to catch twice.
Well, the main concepts have already been developed. I mean, literally, we've gone a lot further than it looks in demonstrating and proving that this protocol works with bits on the wire. Now, what we need to do next is to have a fresh demo, something that is showing the next phase of, like, atomic token transfer across the link, with queued up interactions. So instead of saying bandwidth and, in a forward in time only, sense of streams of things, we say, no, what's really needed to deliver distributed systems is interactions per second. And it's these interactions per second, which is really the kind of like insight. Think of this as one phase commit, two phase commit, three phase commit, and four phase commit.
Yeah.
And
So
when you stitch those together compositionally, then you can give an API to databases and distributed systems that they might be able to use.
So we are on top of the hour, and like any last questions or something? Okay, if nothing, so we can basically adjourn for today's call, and we will have some announcement about a new work stream for next call by Hasham and Dan. Unless they want to give some spoiler, is there anything you want to give, or we just leave it for next call? Hasham?
Yeah, actually, we prefer to do that next call, but in a nutshell, we are looking at hard problems or open problems in time synchronization. Maybe what Paul presented today falls into this category, and we'll
Yes.
be looking for support from the community to address these problems and also demonstrate them, if possible, in relevant conferences and workshops.
Wonderful. All right.
Thank you so much.
Thank you.
Right.
Okay,
Thank
we'll
you,
see you
everyone.
guys in 2 weeks. All right, bye.
Bye.